All right, good afternoon, everyone. Welcome to lecture 18. We're talking about conservation of linear momentum today in a fluid. So section 5.2, and then we're gonna look at mostly examples today, just so you can see how to use this equation, right? It looks a little bit complicated. It's got integrals over control volumes, control surfaces, it's got vectors. So we'll just go through some examples. And then we'll just, at the end, a quick note looking ahead to chapter 12, which is toward the end of the course. All right, but first, just to get us back into things, I don't know how many of you have looked at the discussion question for this week at the beginning of the module, but it's Ant-Man again. And if you remember, the scene from the movie that we watched, I think like lecture 2 or lecture 3, when Scotty puts on the Ant-Man suit for the first time, presses the button, doesn't know what it's supposed to do. He becomes really small, right? And he goes down to the bottom floor of the bathtub, and then his roommate, Luis, comes in, turns on the water. Scotty gets swept out of the tub, right? So we talked about that from the perspective of the interesting physics, right? Because when Ant-Man falls on the bathroom tile, he cracks the tile. So that kind of assumed that he kept his mass, right? But now we want to talk about something else. So here's a sketch I made of the bathtub, and it's a pretty simple problem, right? We've got water coming in on the right from the faucet, and then hitting the bottom of the bathtub and flowing to the left, all the way to the far end where it sloshes against the wall. And I'm asking you to think about this in terms of the forces on the wall. If we know all the properties of this jet from the faucet that's coming in, we know the diameter of the jet, so we know the cross-sectional area, we know the velocity of the jet, so we know the flow rate, we know all those properties. How do we begin to solve for the force on the wall of the tub from the water, right? So it's not just, normally we draw a free body diagram for things and we sum the forces in the different orthogonal directions, right? So some of the forces in the horizontal direction, some of the forces in the vertical direction. So what I want to ask you guys to think about is, can you do that here? Can you just sum the forces in the different directions? And if not, how might you approach solving this problem, right? So basically, just going to put you actually in pairs today, just for a couple of minutes, and I want you to sort of come to a conclusion whether you can just sum the forces in the horizontal and vertical directions to solve for this unknown force on the wall if you know the force coming from the jet. All right, so I'm going to stop the share now. And we're going to go down to just maybe 2, maybe 3 people per room. You're just going to have 2 or 3 minutes this time. So just come to a conclusion on whether you can simply sum forces in the vertical and horizontal directions to solve for the force on the wall. Here we go. And welcome back as you're starting to come back into the main Zoom room here. We've got just about 30 seconds until everybody is going to come back. And then we'll just have a quick poll to see what you decided about whether you can just sum the horizontal and vertical forces here. All right, 5 seconds. Okay, welcome back everyone. So I hope you had some good conversations and were able to agree about whether you can just sum horizontal and vertical forces on the side in this problem. Let's go ahead and see what conclusions that everyone reached. Here we go. So I've got a poll up now and it's asking how can we solve for the forces on the side wall of the tub? And let's see what everyone thinks. Oh, part of the first answer that you're offered got cut off. It's supposed to say just equate the horizontal and vertical forces, it's fine. But the fine got cut off, but that's what that first option is, just equate the horizontal and vertical forces, it's fine. Number 2, sum the moments about an arbitrary point. Number 3, use a control volume approach. All right, we got 95% voted here. I'm going to end the poll, share the results with you, and very happy to report that most of you said that we need to use a control volume approach, right? Some of you said we can just equate the horizontal and vertical forces. That may work in some cases, but in the general case, it won't work. Summing the moments about an arbitrary point would work if you had, if you didn't have to worry about the anchoring forces, right? So that would work, but it can become incredibly complicated. So the simplest way to do this for a fluid is using the control volume approach. All right. Okay, I'm going to switch over now to the annotator. Give me just one moment to do that. And if we have enough time today, we'll go ahead and go over this question in detail if we magically have enough time at the end. But for now, let's go ahead and derive the equation for the conservation of linear momentum in a fluid from a control volume perspective. Of course, if you know a little bit about fluid dynamics, maybe you work in a research lab that's fluid dynamics focused, you've probably heard of the Navier-Stokes equation. So the Navier-Stokes equations, we think, solve for fluid motion in any situation. They're beyond the scope of this course. If you take Fluids 2, ESM 3334, you'll learn the differential analysis approach. It's also in the textbook, although we're not covering it in this course. But the Navier-Stokes equations are Newton's second law for conservation of linear momentum for a fluid, but from a differential analysis approach using differential equations. We're going to do the same thing here using a control volume approach. We're going to apply Newton's second law, conservation of linear momentum, to a fluid, but using different technique, and one that's quite intuitive. All right, so here we have On the right, just a figure of a section of a pipe with fluid flowing through it from the left to the top right. And at this very moment, we've got a fluid system, which, as a reminder, is a collection of specific fluid particles. So if you were to dye them, you'd be able to see them travel through the flow field. We've got the system here, and it's inside the control volume, which is indicated by this orange dashed line, right? So at this very moment, the fluid system and the control volume are coincident. So that's important because that allows us to work with the Reynolds transport theorem. All right. Let's write down Newton's second law of motion for a general system of fluid particles. So here it's that material derivative, if you remember, it's the d by dt term plus u du dx plus v dv dy, etc. And then inside the integral, we've got the vector velocity. So just a reminder, in a fluid, we've got our Cartesian velocity. The vector is little u in the x direction plus little v in the y direction plus little w in the z direction is the general convention, although sometimes you'll see w used in the y direction, etc. We've got our vector velocity, we've got our fluid density, and then we've got our differential volume. And that is equal to the sum of the forces acting on this fluid system. Again, our collection of particles, right? So this is our statement of F equals ma, good old Newton's second law, right? So what does this say? On the left, it says the time rate of change of the linear momentum of the system is equal to sum of the external forces acting on the system. And in a fluid, what's an external force? If you define a control volume, if you define a certain fluid system, an external force would be the pressure force acting on the walls of your control volume or your system. It can be gravity acting on the volume of fluid. An internal force would be something acting between the molecules, right? So we don't count those, van der Waals forces, that type of thing. All right. So another thing we want to note, let's call this equation 1. The next, we want to write down the Reynolds transport theorem, just like we did for deriving conservation of mass. Now, when we derive conservation of linear momentum for a fluid, we're going to write down the Reynolds transport theorem. Who remembers what B was for conservation of mass? When we derived the principle of conservation of mass with Reynolds transport theorem, capital B was m, the mass, so then little b, which is big B, it's the intrinsic version, it's per unit mass, so little b was then just 1, right? Here, it's conservation of linear momentum. So big B is our linear momentum term. It's the mass times the velocity, and little b is then just the velocity. So we take that and we just plug it right into our Reynolds transport theorem from the end of chapter 4, and we get d by dt integral over the system, the velocity, rho, d volume equals integral over the control volume, velocity, density, d volume, plus integral over the control surface, velocity, density, velocity dotted with the unit normal facing outwards, right? Call this equation 2. And just make a note of a couple of things here. So Control volume, of course, is CV. And CS is the control surface. Now let's talk about this little vector, unit vector n. It's a really important quantity when we work with this equation. We have to remember always that it's pointing normal outward from the control surface, right? So wherever you are, the control surface, it's pointing outward. And because we're dotting the velocity with this unit normal outward, it's going to determine the sign of the velocity terms, right? So if we have, like at this entrance section here, if you imagine this was a velocity vector, it's not, it's a force, right? If you imagine this force labeled FD was a velocity vector, we'd get a negative velocity term here from dotting these two vectors, the unit normal and the velocity vector, right? If they were pointing in the same direction, we'd get a positive term. So that's going to come up all the time in these types of questions. So what does this say? It says the time rate of change, first term on the left-hand side, time rate of change of the linear momentum of the system is equal to the time rate of change of the linear momentum of the contents of the control volume, plus the net rate of flow of linear momentum through the control surface. That's what these three terms represent. Just noting that at this moment in time, again, just noting that the control volume and the system are coincident. So what does that mean? That means that the sum of the forces on the system is the same as the sum of the forces on the contents of the control volume. All right, so if we now combine equations 1, 2, and 3, we get that the sum of the forces on the contents of the control volume is equal to this integral over the control volume, right? This unsteady term that usually goes to 0 in practice, plus the integral over the control surface, which is the main term that we're going to be working with in this equation. So here we have it, the celebrated conservation of linear momentum, the linear momentum equation. This is Newton's second law for a fluid. So this is equation 522 in the textbook. And it's valid for any non-accelerating coordinate system, and that's just true of Newton's second law in general, right? So you can have a coordinate system that's fixed in space, you can have one translating through space on a straight line with constant velocity. You can't have an accelerating coordinate system, because if you do, then Newton's second law in this form is not valid. All right, so there we go. That's the equation. It looks a lot like the conservation of mass equation, but with an added velocity vector in the terms now, right? And of course, instead of the two integral terms summing to 0 like they do for conservation of mass, now they sum to the sum of the forces, right? Any questions about this linear momentum equation before we move on to some examples? All right. I hope you guys are doing okay. I'm noticing that we've got about a little fewer than half of the number of people tuning in today than we did on Monday. And so I'm guessing that you've got lots of stuff due before fall break. And I'm just sending you good wishes that it all gets done and it's easier than you thought. Okay. Right, let's look at our first example. You're welcome, and wish the same to me too, please. This semester is extra challenging for everybody, for sure. All right, so here we have a horizontal jet of water coming in from the left and from a nozzle and striking this water vane, right? And the water vane has some angle theta that it turns the jet through, right? So we're given the velocity here from the nozzle, we're given the cross-sectional area of the jet, and then we're given this angle theta. We're also told that the speed of the jet is 10 feet per second, and we want to determine the anchoring force needed to hold the vane stationary if gravity and viscous effects are negligible, okay? So one thing I want to just note before we start on this problem, I'll actually go back to the previous page. If you look at this sketch, one thing that really strikes you is that, oh my goodness, when we draw a control volume now for conservation of linear momentum, we're drawing a free body diagram, right? We're going to be drawing the control volume, and then we're just going to draw in all the forces that act on the control volume. So we are drawing our free body diagram. So we're going to draw in sometimes, pressure forces acting on the sides of the control volume, maybe the weight of the fluid inside, maybe some applied forces acting through solids, maybe some viscous forces. But essentially just keep in mind that now that we're dealing with conservation of linear momentum, these are free body diagrams that we're drawing when we draw our control volumes. That said, you need to choose your control volume wisely, right? So we have lots of choices here. So you're brand new to this, so you probably think, well, I don't have no idea where to draw my control volume. Maybe I'll enclose the fluid, just the fluid in the control volume, right? That would be an excellent choice, except for the fact that what we're asked to solve for is the anchoring force needed to hold the vane stationary, right? So we need to know, like, this is the vane, this pink shaded thing, what force do we need so that it doesn't slide along the ground or, break free? So we have to include the vane. And the really cool thing is you can do that with a control volume. You can just slice right through solids and solve for forces in solids. So we're going to do that. And we're going to be a little bit smart about it. We don't want to make life hard for ourselves by choosing a control surface that is not perpendicular to a flow direction. So we're going to just sort of box. Oops, let me use a different color here. Use the red. We're going to box in the vane. We're going to cut right through it because we know we want the reaction force. But then when we get up here to this top right corner, we're just going to go ahead and make that corner of the control volume at a different angle. We're just going to cut that corner out so that the control surface right there is normal to the direction of the flow, just to make life easy for ourselves. And you should do that whenever you can. All right, let's draw in some forces. So we'll draw in those anchoring forces that we're asked to solve for here. We'll call it FAX and FAY. We've got V1 here. We've got some V2 here. Keep in mind, again, that the unit normal is facing outward everywhere at every surface of this control volume, right? And I think that's all we want to note for now. We'll just note the X and Y directions and just mark that this is section 1 here and this is section 2, the exit. All right, so we'll go ahead and apply. We'll write down the conservation of linear momentum equation here. Um, so we'll, instead of writing it down using it in vector form, we'll just go ahead and write in the components. And even though I just said on the last page that it's usually u in the x direction, v in the y direction, w in the z direction, here we've just got a two-dimensional velocity field. It only depends on the x and y direction. So we're going to use u in the x direction and w in the j direction, just because it's a little bit easier visually to distinguish u and w than it is u and v. All right. So we've got that first term d by dt over the control volume of, now instead of vector velocity v, we're just going to write in the x component, because we're dealing with the x component of the conservation of linear momentum equation. So u rho d volume plus the integral over the control surface of u rho. Now note, here I'm not subbing u, the x component of the velocity, for the vector velocity. I'm keeping the vector velocity. That's because we need to be really careful about this dot product to figure out what sign the term gets. So we're going to treat this with a little extra care. All right, so here's the x component, and then we've got the y component. And this is equal to the sum of the forces in the y direction. Okay, so anything that we can get rid of right away? Any ideas? We can make one sort of simple, reasonable assumption and cross out two of these terms right away.
V dot n should be 0.
Are you talking about the first terms here? Sorry, you got cut off a little at the beginning. Are you talking about the d by dt terms?
The second term in both equations, the v dot n hat should be 0.
Oh, okay. That is 0.
Or it should be 1. I mean, it should be 1.
It should be 1 in most cases, and then we're going to deal with sines, and you're absolutely right. We're going to deal with sines and cosines in a little bit.
Did it know for the first term is 0?
Yes, you said this term, right?
Yeah.
Yeah, that's right. So you're absolutely right. And I'm sorry, your names aren't popping up, so I can't credit you. But we can assume that it's steady. So we can just immediately cross out these first two terms. Right, so very reasonable assumption that it's steady. So now we've just got these terms, and let's remind ourselves physically what they represent. The right-hand sides are easy to understand. It's the sum of the forces, right? We talked about how when you draw your control volume, you're drawing a free body diagram. Well, sometimes we would have pressure forces acting on the control surface, but here everything's open to the atmosphere. We can assume we have a free jet. In other words, the pressure inside the jet is just atmospheric, because we don't see the jet spraying out when it exits the nozzle or narrowing, right? It just has the same width as it leaves the nozzle. So we know it's a free jet. We know that the pressure in the jet is just atmospheric. Up here, we see the same thing, right? We don't see anything. It's not leaving a container or anything. So if that's true right when it leaves the nozzle, it's certainly true up here. So we're just dealing with atmospheric pressure everywhere. We might have a change in pressure due to height, but we've been told to neglect the effects of gravity. So any hydrostatic effects are negligible, right? So since that's the case, we don't have any pressure forces acting on our control volume. We might sometimes consider the weight of the fluid in the control volume, but again, we've been told to neglect the effects of gravity, so we're not including weight. We've also been told that viscous effects are negligible, so there are no friction forces, right? So the only forces we have are these two anchoring forces, and that's going to come into the right-hand side. And then we've got these terms, and remember when we derive this equation, this term represents the flow of linear momentum through the control surface. That happens in two places, at the entrance here at section 1 and at the exit here at section 2. Now we just need to write down the correct form by taking the dot product here correctly and getting the signs right. So let's go ahead and do that. So let's call this equation 1, equation 2. So we simplify 1 a little bit. We're going to see, we're looking now at the exit. We've got this v dot n. Looking at the exit, we've got u2, right? So the assumption here is that we've got v1 equals u1 in the I direction plus w1 in the j direction. v2 equals u1 in the, u2 in the I direction plus w2 in the j direction, right? So we've got inlet and outlet. And I mean inlet and outlet of the control volume, right? So those are our velocities there. They're still vector expressions, right? So if we simplify this now, if we look at the outlet, section 2, in the x direction, we've got u2, rho, a2, v2. Now v2, v1 is just the magnitude of velocity vector 1. v2 is the magnitude of velocity vector 2, right? So notice, all right, so we've got the term that accounts for the flow of linear momentum carried by the stream at the exit in the x direction. Notice that this is a positive term, right? Because v2, that vector velocity dotted with the n here, those two vectors are pointing in the same direction. So we get positive 1 when we dot them, not negative 1. Well, we get positive 1 times the magnitude of v there, right? However, in the x direction, when we look at the flow of linear momentum through the entrance, here we have a velocity vector pointing in and unit normal pointing out. So we get this minus sign, okay? We get minus E1 rho A1 V1 equals sum of the forces in the x direction. We can do the same thing for the y direction equation. Get W2 rho A2 V2 minus W1 rho A1 V1 equals sum of the forces in the y direction, right? And we have that minus sign on the second term for the same exact reason. When we come over here at the entrance, we see that the unit normal and the velocity vector are in opposite directions. So when we dot those two vectors, we get that minus sign out. All right, now we've neglected gravity and viscous effects. So by the Bernoulli equation, V1 is equal to V2, and I'll step through that. Right, so we have P1 plus 1/2 rho V1 squared plus Z plus P2 plus 1/2 rho V2 squared plus gamma Z2, right? So here we've been told to neglect gravity. And we've already determined that the pressure is the same. So we can see that V1 or V2 equals V1 equals 10 feet per second. Whoops, I wrote meters. All right, so that's where that assumption that V1 equals V2 comes from. It comes from the Bernoulli equation and the fact that we're neglecting gravity forces and viscous forces effects, right? So what Bernoulli tells us is just that those two terms containing the velocity are the same. The 1/2 rho v squared terms are the same, and since rho is the same everywhere, we know that the velocities are the same. All right, so at section 1, U1 is equal to V1 and W1 is 0, right? At the entrance, there's no vertical velocity component. At 2, at the exit of the control volume, U2 is equal to V1 cosine theta. W2 is equal to V1 sine theta. Okay. So now we can rewrite again equations 1 and 2. I'll call them 1 and 2 double prime now. And we get V1 cosine, cosine theta rho A2 V1 minus V1. Well, I'm just gonna, running out of space, so I'm just gonna write it compactly. V1 cosine theta rho A2 V1 minus V1 rho A1 V1 equals the horizontal anchoring force, and V1 sine theta rho A2 V1 minus 0 rho A1 V1 equals the vertical anchoring force. So we also have from conservation of mass that A1 V1 equals A2 V2. We already know that the velocities are equal, so this implies that A1 is equal to A2. And this allows us to finally simplify, rearrange, and solve for these anchoring forces. So in the horizontal direction, we've got minus rho A1 V1 squared, 1 minus cosine theta. If we plug in our numbers, it's minus 1.94 slugs per cubic feet times 0.06 feet squared times 10 feet per second. Oops, this square should go inside. Times 1 minus cosine theta. So that's minus 11.64, 1 minus cosine theta pounds. Ooh, squeezing it in there. Now, what does that minus sign tell us? What does it mean to have a negative force?
Opposite direction.
It's the direction, exactly right. And again, sorry, your name's not popping up, so I don't know who that was, but that's right. Right, so we drew in FAX this way to the right and FAI upwards. So we drew them both in the positive direction. It turns out that the anchoring force in the horizontal direction actually acts to the left. That means that you need to push on the vane to the left to get it to stay in place. And conversely, the vane needs to push on the fluid to the left, right? Because the fluid is pushing it to the right, or trying to push it to the right. Good. Okay. And then finally, we will write down the vertical anchoring force, or FA. I'm mixing A and Z subscripts here, aren't I? Let me see. Yeah, just here. We'll call that Y. Good. Okay. It's equal to rho A1 V1 squared sine theta. Or if we plug in all the numbers, I'll sort of skip the details, 11.64 sine theta pounds. Right? So it turns out that the anchoring force is vertically upwards. The vertical component of the anchoring force is vertically upwards, right? So a lot to think about here. We've solved for the force acting on the fluids, acting on the contents of the control volume. So remember, we just derived the equation of linear momentum, and it is for the forces acting on the fluids, right? Not the force that the fluid is exacting on the vane or anything like that. It's the force acting on the fluid. So we have to think carefully and sometimes apply Newton's third law, right? That forces, that there are equal and opposite reaction forces sometimes to back out what the right direction is, right? So here we've solved for the force that the vane is actually exerting on the fluid, which turns out to be the right thing, the thing that we're solving for here. A couple interesting things, if you note the expression for the forces, it depends on theta, right? So now what happens if theta is 0 degrees?
There's no forces in the y direction.
Exactly. If it's 0 degrees, then the water is not turning at all. It's just sliding now across a flat surface. There's no forces in the y direction, but also in the x direction, right? And that's because there's no friction force. We assume that viscous effects were negligible. So there are no forces at all. It just slides right across. What about if it's 90 degrees? If it's 90 degrees, there are both components of both forces, and it turns, the water gets turned 90 degrees. What about the interesting case where the vane is actually 180 degrees, so the water comes in and it gets turned right back around and sent back in the direction it came from? Do we have both force components here in that case?
We just have the x component.
Exactly. So we have a really large x component and we have no vertical component. And that makes perfect sense if you think about it physically, right? You've got this water velocity jet coming in and you've got to apply some force in the opposite direction to get it to turn around and go in the opposite direction. You don't need to apply a vertical force on the mean, right? So that's what we see there. All right, any questions about this problem? Let's move on. I want to start on this one, although I know we're not going to be able to finish it, because this has got a lot of interesting properties. This problem, the last one didn't. The last one basically made all these simplifying assumptions. No viscous forces, no gravity, no pressure forces. Here we've got water flowing vertically upwards through a pipe, and we do have viscous forces from the walls. We do have gravity forces, so we have to take into account the weight of the water, and we do have pressure forces, right? We've got a cylindrical control volume here. At the bottom, at the inlet to the control volume, we've got a uniform velocity, but then at the top, we've got a non-uniform velocity. We've got a parabolic velocity profile. So I just want to set this problem up for now, just so we can talk about how we deal with these different forces, and then we'll probably be out of time, but I'll finish out the slides before I upload them. So here, and interestingly, here we do have pressure forces acting on the control volume, right? Because we're not out sitting in the open atmosphere, we're in a container. So we have to think very carefully if the pressure is at the same at both ends of the control volume. By the way, this is a familiar problem. We looked at this problem in lecture 15 last week, and we solved for the formula velocity profile. So let's just go ahead and set this up. You can see that the control volume has already been sketched out in a red dashed line. You can see that at the entrance to the control volume at section 1, we've got this uniform velocity with magnitude W1. And then up at the top, we've got W2, and it's given in terms of W1. We actually solved for that, why that's true, in lecture 15. We're given the weight of the water column, and we're given that the friction force, the force on the fluid from the friction at the walls, is RZ. And we want to develop an expression for the pressure drop that occurs between sections 1 and 2. So let's just set this up. So again, we're going to use, of course, conservation of linear momentum. In the last problem, we used the X and Y components. Now we're going to use just the component along the axis. And if you look at the coordinate system here, that's the Z component. We're just going to assume right off the bat that this is steady flow. We're not even going to write down that d by dt term. We just know it's 0. It's not even going on the page, right? So we'll skip right to those terms that represent the flow of linear momentum across the control surface. So we've got one term like that, because this is a one-dimensional flow. And then the forces in the vertical direction are the pressure force on section 1 at the bottom. We've got that uniform pressure P1 times that area A1. And that's in the positive direction because pressure always acts inwards on the control volume. If you remember that from chapter 1, pressure force is always acting inwards on any object, including a control volume. And then we've got that friction force RZ, which is clearly pointing down, so that gets a negative sign. We've got the weight of this water column, which is clearly pointing down. It also gets a negative sign. And then because the pressure always acts inwards, the pressure force at section 2 also gets a negative sign. Call that number 1. And remember, all these forces are the forces acting on the contents of the control volume, so acting on the fluid, right? And that's always the case when we're dealing with conservation of linear momentum. All right. So we've set that up. That's how we're going to step through the problem. You know, we can go ahead and simplify from here, and I will do that before I upload the slides, but we've got just 2 minutes left, so I'm going to move on. And I want to make a note on this moment of momentum equation that also shows up in this section. If you take R cross the linear momentum equation, you get the moment of momentum equation. And we're not going to see that at this point in the course, but when we deal with turbo machinery in chapter 12, we're going to use this all the time. All right, finally, just wrapping up, looking forward. You guys have fall break on Friday in 2 days, so Hyungun is just going to pre-record and post his session. There'll be no live session. Same thing, he'll have his usual office hours tomorrow, but his Friday office hours are canceled. Because you're missing the day on Friday, I'm moving quiz 8 and homework 8 back a day, so instead of being due Sunday night like usual. They're due Monday night at midnight. Midterm 2 is Wednesday next week, so in a week from today. I will post a practice exam as your extra credit assignment for next week. It's going to cover hydrostatic forces on curved surfaces up through the very beginning of the control volume stuff that we've been looking at. Your homework for the following weekend, homework 9, is going to be very light because we won't have covered a lot of new material. And then just looking ahead 2 weeks, or a week and a half now, your video project proposal is just a really brief, short description of what you're planning to do, just so I can vet it, are due then. And that there's going to be an assignment where you can upload your proposal showing up in Module 9. Are there any questions about any of this? No. All right. Well, hang in there, everybody. I know it's a rough week. Wishing you strength, and have a good week. Have a great break. I hope you get refreshed and recharged. And I will see you guys on Monday.
Thank you.
Thank you.